All right, so let's continue the review here. We're on 3.8. We're talking about representation of solutions. One of the key points of this particular section, as we've mentioned already in class, is that you're going to be asked to represent some of the solutions. So what we're dealing with here is we're going to be dealing with particulate diagrams. Okay. So the main thing that you want to remember with the particulate diagrams is you want to make sure that you're able to identify the solute. And if it breaks down into ions, make sure that you can identify those ions as either the positive ions or the negative ions. You also want to make sure that you are able to represent the ions here when they're generated in the proper size. Make sure that it's the correct size. Remember here that cations are typically smaller and the anions are typically larger than their corresponding cation, partner. So those are two items that you want to be able to remember here. And then the other item with regards to particulate diagrams is that you also want to make sure that you are representing any orientation of, say, the solvent molecule. And in this particular case, the molecule that we're looking for here is water. Make sure you're able to represent it properly. As before, we know that the water molecule has these kinds of arrangements, negative on this side, positive at the bottom here. So we have a polar existence overall for the water molecule. And it's just making sure that you place the water molecule around any solutes, ions that are generated, you put them appropriate. So that means, what that really means here is that you're going to have the water facing the cation, or the oxygen facing the cation, and then the hydrogen atoms are going to be facing the anion. And so that's one important thing there. The other item that I did not mention over here is not only is it important to put the ions of the right size, but you want to make sure that you're also representing the ions here. I'll put this as a second link over here on the far right. You want to make sure that you identify the charge of the ions. And so that goes for both the positive or the negative ions. So just make sure that that's something that you're doing overall. There were 3 parts that were involved overall in solubility. So when we represent a solution, remember we are adding a solute. Is going to be added to a solvent. So we're going to add this to a solvent. And the end result here that we're going to get is we're going to wind up getting here a solution. And so that solution, you want to make sure that you represent accordingly. So the most common thing here is putting all of this together is that there are phases here. When you talk about the solute into the solvent, this solution is actually going to go through 3 parts. The first part here is going to be where the solute it's actually going to break apart. So we'll do it like that. In fact, let me make some more space here. Let's make some of this here. Let's move some of this over here to the right. Move this up a little bit, and then we'll continue to write there. The other item here is going to be that the solvent is going to accommodate that solute. So we'll call that solvent accommodation. And let me go ahead and erase this a little bit, clean it up a little bit there. So you got solvent accommodation. And then the last step of all of this is the solute is going to have an interaction with the solvent, or maybe not. And so we'll leave this here as interactions. Now, it's important that you also recognize in our discussions in class, the solute, there are pretty strong inner molecular forces of keeping the solute intact. So if we're dealing with a solid, the solid then is going to have a pretty strong intermolecular force. Maybe there's some London dispersion forces there. Maybe there's some polar bonding going on or some polar attractions occurring there. And so the solid doesn't necessarily want to break apart. It's going to want to stay together. So one thing to remember in this regard here is that the solute, as it starts to go through this process of breaking apart, this is actually going to be very endothermic. So we can just do that, endothermic. So you're going to have to add energy to that. There's a lot of energy that might be required there. So it's really not going to occur quite well here in terms of breaking apart initially in this first phase. So you have to add some of that energy. So that energy can be obtained from the environment, but the intermolecular forces are definitely going to be something that you want to take into account as you start looking at this. The second item is in the accommodation that is occurring here in the solvent part. This second phase, and let's kind of color code this in blue, the second phase here is going to essentially ask you to kind of think about the arrangement of the water. There is already an arrangement of that water in alternating fashion. So you've got positive, minus, all the way around here for the arrangement. And I'm not going to redraw all of the water molecules here for you, but you understand that each of these here corresponds to the arrangement up here. So the negative side would represent the oxygen atom at the top. So maybe at the very least, I might draw one here for you. And so here what we've got is the alternating pattern that we'll see here is going to be here. If I have a water molecule and like that, and so you would see here in this particular case, this would be a negative side here, and then you've got the positive side on this side, repeating itself. And so let's put that right here in the center. And so that's what these regions are representing here. So when you see a negative sign here in the structure, we've got an oxygen atom, and on the positive side, you've got the hydrogens. And so if I draw those in there so you can see that, you got an oxygen here, hydrogen and a hydrogen, and then it's the other way around. Let's draw that in yellow. So coming up the other way, so you have it like that. And it's an alternating pattern. And when you've got this alternating pattern, there's already in that water, there's already hydrogen bonding occurring. There's some London dispersion forces occurring that are keeping the water molecules together. And when a solid is introduced into the mix, it's going to disrupt this. And that's not going to be something that's desirable or even advantageous for the water. If you look at it from the water side of things only, what's going to happen here is that the water has to move and make room for the solute. And this particular section here is going to wind up being another form of energy requirement. So what you're going to have here is another endothermic event. So this is going to require energy in order to take place. Now, the last part here, when the interaction takes place, you could have a very strong interaction between solute-solute. You can have a very strong interaction between solvent-solvent, or you can have a very strong interaction between solute and the solvent, which is what I've kind of already indicated here. If this interaction is the strongest, this actually is going to lead to a very positive outcome, and this is going to wind up being exothermic, depending on the strength of that attraction that's occurring there. So if the attractions are high, it's definitely going to be exothermic. However, if this, let's just put it here, high attractions, because that's what's going on here. If there's a high attraction, you'll get exothermic. However, if these attractions are low, so what this is going to wind up being is it's going to wind up being closer to endothermic. And that there is a significant point to consider, especially when you're trying to represent all of this in some kind of diagram. So if you look at the notes, a lot of that was addressed already in the notes. But here the main thing, though, when you talk about the solution being formed, the solubility process is actually related to this attraction. So solubility is actually a product here of a high solute to solvent attractions. And yes, you could say things like the polar is going to dissolve polar solutes, or polar solvents dissolving polar solvents, and vice versa for the non-polar side. But really, if you want to explain it, the proper way to explain that would be to focus on the attractions. And in this particular case, solubility occurs between solid and solvent when the attractions between those two are the highest. And so that's really the main thing there. One other item that you'll be asked to do here is to represent things. So remember, we had already said at the very beginning here, we had talked about the diagrams needing to have the size. And so let me see if I can make this a little bit smaller, make some room for us. Move this over here. Let's bring this over here to the front. And so the main thing that we were looking at here at the very beginning was looking at making sure that you can represent things a little bit better with regards to the ions that you draw. Make sure that you have the positive and negative ions, that the size is properly drawn, and that the ions charges are identified properly. And then the orientation of any solvent. You want to make sure that that's there. And so let's take a look at a very quick example. This was also in the notes, but let's go ahead and show you now here. So let me move this out of the way again. And let's move this other one over here to the side. And let's take a look at the example here of, we had looked in already in class the sodium chloride example. So let's do another one here. Let's go ahead and take something like magnesium chloride. And so here, magnesium chloride, if we represent this, here magnesium will break apart. If this particular, let's say that it's aqueous, it's going to dissolve. So we'll have a magnesium part, and we're also going to get a chlorine part. The chlorine here, because of the subscript 2, that means we're going to need 2 copies of the chlorine. So we'll draw 2 of them there. Let's put them in the same color. And they're both negatively charged, so -1, -1. The magnesium here, because the magnesium is over here on the cation side, it actually is going to have a copy, one copy here is going to have a charge of a +2 charge. So we'll go ahead and put that there as a +2. So we know that the cation is going to be represented a little bit smaller because it is actually losing electrons. And so remember that the positive here loses electrons. And so therefore here, this is going to be smaller. When you represent it on the negative side here, this is going to gain electrons, and so we should represent that slightly bigger in comparison. So in this particular case, if I'm drawing a representation of these 2 molecules, let's say that I'm going to use a circle for the magnesium, and let's say that I'm going to use a triangle for the chlorine. I want to go ahead and use those appropriately. So since I know that the magnesium is going to be a little bit smaller than the chlorine, when I represent that, I'm going to go ahead and represent that here with a circle like that. And if it's the chlorine in ion form, I'm going to draw the chlorine just a little bit bigger. And so let's see if I can do that like that. And then I'm going to go ahead and make a copy of this. And so there's my 2 copies here. I got to make sure that I go ahead and put the charges here. So I want to put +2 there and a -1 and a -1. Now, you don't have to put the numbers for the -1. You can just reuse negatives. But this here would be representative of a 1 molar solution. So let's say that we had 1 molar there. We would use that. In the case that we had, say, a 2 molar solution here instead of a 1, let's go ahead and represent that as a 2. And so let's say we got that there. And so just to make sure that you follow along, I'm over here at the very top left corner here. We've got 2 moles. So the way we've drawn it here, it only shows 1 mole. So the ratio here, I need to have 2 magnesiums. I only have 1. So what I'm going to have to do here is I would have to come in here and just draw another copy. And then I can have it like that. And so that would be the proper representation of magnesium chloride in solution. And so the overall number then corresponds to what it is. Notice the size is identified properly in terms of cation, anion. We have the charge identified. We do have the ions identified. If you want to take it a little bit further, you can also just use a key, or you can actually designate here in terms of name. You can come in here and you can say magnesium, and then you can say chlorine here. For each of these, and represent them like that. But if it's a particular diagram, really there's no need to have all of those there. So typically you wouldn't have to have them. So I'm going to go ahead and erase them here from this, but you could put them there like that. And so the bottom part here is the final representation that we would have that corresponds to magnesium chloride. That's pretty much the highlights of this particular section, 3.8. So if you have any questions, see me in class. Otherwise, we're going to keep going. In the next video, we'll address 3.9 in the review.